geodesics. So I have two papers in this topic, which really relates to origami and Kirigami, mostly to Kirigami, not origami. So just a few pictures in the first slides. And by the way, my talk, there will be, like one lemma and one theorem, but very little formulas. So maybe good as the last closing talk of this very successful and very much full of beautiful math and complicated math day. So origami describes rules for creating folded structures from patterns on a flat sheet. So Japanese terminology words come this word origami. Ori means folding and kami means paper. So now kirigami, kirigami is basically origami but adding cuts. Again, terminology comes from the Japanese. Kiri is cutting and gami is paper. So these beautiful pictures here come from a paper published in, I guess this one in Nature 2 years ago, and it's due to comes from the lab of my collaborator actually on this project, who is Han-L-Mahadevan. And so basically what they do, they say, we want to find a sort of discrete approximation. We want to manufacture surfaces. So maybe you want to create a bowl like this, or some cone, or like a double bowl here. So what they do, they claim to have an algorithm. There is no theorem really, behind it, but there's a concrete formulation, concrete algorithm, in which on a flat sheet of paper, they create cuts, okay? And then what happens is they basically grab this this square or this cutted rectangle on two sides, and then they extend, they pull. So when they pull, of course, if you pull just on a piece of paper without cuts, you cannot do anything, it's inextensible, okay? But when you have cuts, when you pull, the cuts are going to open up in some way. And the catch here, which is really beautiful, is the Theorem algorithm, which makes the cuts in such a way that when they pull, they obtain, you see, like a discrete version exactly of the surface that you want to obtain. So you get like a bowl, of course, with holes here, but then when you dip it inside some solution, the holes are going to be patched up, and hello, you get what you want. Instead of hammering and pulling and, manufacturing it some complicated way, you just apply the cuts, you pull, you dip, and you get what you want. Okay? Very nice, very cool. So they observed that varying, now don't ask me about, or maybe ask me after the talk, what happens in this paper, but like one of the key observations that they made is that varying the shortest path, which later in my talk I will be calling the geodesic, that's the geodesic, rectifiable geodesic. Okay? So varying the shortest path between the points at which you pull, okay, influences the deployment trajectory of the sheet. So let's say not only we are interested in the final discrete approximation of the original, hopefully approximation of the original surface, but we also care about the trajectory. So what kind of, I call them discrete surfaces you are obtaining along the way while you are pulling until you cannot pull no more. Okay? So this shortest path, the structure of this shortest path is of essential importance here. So we want to study the structure, we want to study the geodesics in Kirigamized sheets. Two observations they make. Okay? The first one, so take a here is the simplest Kirigamized sheet. Okay? I have just one cut, which when you pull is going to open up. Okay? Here you have a few more. Again, when you pull, you are getting some sort of cuts like this. So they make the first observation, which is the geodesics in a planar sheet with cuts are always piecewise linear. They are polygonal. That's a simple observation to make. We will come back to this with more pictures in my next slide. But another observation they make is that this, so you can pull, you pull until you cannot pull anymore, and then all the geodesics are simultaneously rectified. You understand what I'm saying? So you take, in this picture here, you have two. You apply the force here, you apply the force here. Just one single cut. how many geodesics I have. Let's say this cut is in this particular picture precisely located in a, so that the picture is symmetric. Okay, it's exactly at the center. So you have one geodesic and one geodesic here. You have two geodesics. When you pull, those two polygonal geodesics are going to become a straight line, a segment, and then you cannot pull anymore. So they observe the same, this is very intuitive, very natural, no matter what crazy pattern of cuts, they can be intersecting, long, short, millions of them, okay? No matter what crazy pattern of cuts you imprint in the sheet, when you will have lots of different geodesics, when you pull, there is like no geometric obstruction in between. So when you pull, all of them are simultaneously rectified. So then Maha asked me, can you prove this? So basically here my talk, I may end my talk. The answer is yes. And that's the theorem. So for the plan of my talk, I'm going to introduce some mathematical formalism, then I will present the theorem, and then I will present a sketch of proof of this, of existence of an isometry, which simultaneously rectifies all the automatically piecewise linear polygonal geodesics in this context. And maybe one thing why you shouldn't like say, oh, okay, that's it, we now know how to talk, is that my algorithm, our construction is constructive. That is, it's not just an existence theorem, but we have a precise formula. We tell you where all pieces of this Kirigamized sheet, where they go in this isometry. Okay, so that is the formula. Okay, so here is the formulation of the problem. So we have an domain omega in R2, and in this domain I'm going to be given a graph which consists of vertices and edges. Okay, so no, it's not a complete graph. There are some edges and some other edges are not there. So those edges in my mind are going to represent the cuts. Okay, so by capital L I denote the set of edges of this planar graph, and this is the set of cuts. So now without loss of generality, this is a planar graph. That is the edges do not intersect. Of course, if the cuts intersect, that I'm going to introduce an intermediate point from which, let's say, 4 or 5 or 15 cuts emanate. So without loss of generality, I can assume for my picture that the graph is planar. So these are some examples here. So cuts will be always here represented by lines, purple lines. And we have the following definition. So given 2 points, P and Q, distinct, in the same connected component of omega set minus L, right? So omega is this planar domain, and I have a set of cuts in between. Of course, the set of cuts may disconnect the domain. So let's take 2 points which are in the same connected components. So then I compute the distance, geodesic distance between them. This is just the infimum of the length of, say, piecewise C1 curves, which emanate, which start from P and end at Q, and they avoid all the cuts. It's very nice definition. And then we say that the curve is a geodesic, provided its length is exactly represents this distance defined here, and it is the uniform limit of a sequence of piecewise C1 curves which completely avoided the cuts. So this is just because my cuts are closed segments, so the geodesic in fact may intercept the cuts at the endpoints of the cuts. So the geodesic itself does not completely avoid cuts because it may touch them at the endpoint. So in this picture, again, very simple picture. So here, right, this is P and this is Q. There are again 2 geodesic. One goes like this, one goes like this. In this picture, I have 2 cuts and I have 3 geodesics. Okay, the first one is like this. The second one goes down, so it's like 1, 2, 3 lines, and the third one goes like this, and like this. Okay, it is the picture is just arranged in a manner that I have exactly 3 geodesics. In this still quite symmetric picture, I have 1, 2, 3, and 4 geodesics. In fact, anything is possible. Okay, so if you ask me if I have this P and Q, must the geodesic always sort of be outside of the cuts? No. So here both the purple and the blue line is the sequence of cuts. Okay, so I may have cut just a sequence of cuts arranged like this. So then to go from P to Q, You go like this, and like this, all the bottom geodesics. Here I have tons of different geodesics, okay? There is actually 5 of them. Here I go from P to Q like this, and maybe like this outside. Okay? Very complicated. So here are 2 theorems that I want to present. First one is really a lemma. That's how it's called in the paper. So in the context that I presented, I take this P and Q, then there exists at least one geodesic from P to Q, and each such geodesic must be a finite polygonal. Okay, so it's a polygonal with all its vertices distinct and coinciding with the vertices of the cuts. So basically, that is what we've seen on the previous picture, right? So the geodesic always turns at the end point of some cut. So this is nothing, that's just an observation. And the main result is theorem 2, which says that there exists a continuous and piecewise affine map from the Kirigamized sheet into map 3 with the following properties. Property 1, U is an isometry, so almost everywhere the distance. Fancy when you say it's an isometry. Okay. And property 2, for every geodesic from P to Q, the image of this geodesic under U coincides with one and the same segment from the image of P under U and the image of Q under U, and the length of this segment equals to the original geodesic distance, which is the length of every geodesic under consideration. Okay, that's it. That's theorem. Questions about the statement of theorem? So now I'm going to show you the proof.
Actually, I do have a question.
Yes,
So, you said that all the cuts are, so all the geodesics are put into straight lines at the same time.
yes.
But is that stated in there? Because you're just saying that the image at the end they're all straight line segments, but one could become a straight line segment before, right?
One
could become a straight line segment after, let's say, half the time and then stay there.
Oh, there is no time here. There exists, so maybe that's a bit confusing. In the beginning I said that in that procedure with the fancy pictures, they look at the trajectory of deployment. No, I'm just saying that the end isometry, I can prove mathematically it exists. It has the properties that they see this in their experiments.
I misunderstood a little bit what you
Okay,
said.
so there is no geometric obstruction. So in fact, yeah, you start with this, you pull until you can pull no more. And then what happens? Then really you have an honest isometry, and the image of all geodesics are one and the same segment. Somehow, if the pattern was an easy pattern, you can see. But if the pattern is crazy and strange, who knows what happens in between those cuts? Maybe it's what I call it the geometric abstraction that you cannot really do it. You cannot pull up to the maximal distance because something happens along the way. Okay? So the statement is no, this does not. So this is really the proof of theorem 1. So there is a path-shortening algorithm, which is pretty obvious. You take P and Q, you have a bunch of cuts here, you take a curve, and then you shorten this curve by replacing its part in a consecutive order, replacing them by straight lines. Okay, so first you have this curve, and you go from P, you start emanating rays from P along this curve until they touch the set of cuts for the first time, and this is the first segment that you keep put. And then you continue. So then you look at this remaining piece of the curve. You start from P1, and then you continue until you again touch the set of cuts. So this is your second segment, and then you continue like this until you have a polygonal, which of course is again a polygonal joining P and Q, but its length is shorter than the length of the curve, and then basically you choose, there is only finitely many of such guys because you can also check that they are non-intersecting automatically, so they have no self-intersections, so then the shortest of them will be, there's just finitely many of them, will be exactly the geodesic, minimizing curve, and it's automatically polygonal. Okay? So now really that's the point of my talk, is to sketch the proof and the construction of this isometry rectifying all the geodesics in Theorem 2. Okay? So that's the statement of the theorem again. And the proof comes by an algorithm. And here are the main steps in the algorithm. The first step is sort of, you may think, counterintuitive, because the more cuts you have, the more degrees of freedom you have. But in the first step, I'm going to seal certain portions of cuts, which I declare inessential portions of cuts. So these are the cuts which can be sealed, but they do not change the global picture and the onset of my result in relation to the geodesics and the existence of rectifiable isometry. Okay, you will see what I mean by this. Then when you seal those inessential cuts, you obtain a stable configuration of cuts. That is, your graph, which represents the cuts, becomes a forest. So it has no loops. So this graph becomes a finite number of trees. Okay, a tree in graph theory is a graph which has no loops, but it is connected. So then it turns out that we can order the geodesics. There is a natural partial order relation. And we can also order the remaining cuts, which now form a new planar graph. And then we will construct the isometry on each region. There will be two different types of regions between two consecutive trees and inside a given tree and between two consecutive geodesics. So there will be like a lexicographic order on the regions which are enclosed between those trees, the pieces of the graph, which represents the cuts, and the geodesics. And on each of this region, I will explain exactly what I do, what is the procedure for obtaining the isometry. Okay? And then we will construct on regions within each tree and between consecutive geodesics, and at the end of the day, there is a construction on the exterior domain that is somehow outside of the smallest geodesics and the largest geodesic in that partial order relation, which can be defined precisely due to the stability, to minimizing the set of cuts. Okay, so step one, cut sealing procedure. So assume you have the following, okay, so this is P and this is Q, and you have cuts like this. And they are ordered, so order the cuts in some way. So here, of course, this is not unique. So here L1, L2, L3, L4, L5. But look at this picture, it's exactly the same configuration. I guess this is L1 is horizontal like this, L2 is vertical here, L3 is another vertical, L4 is this diagonal, and L5 is here. So what you do, you take the first of the cuts and you start sealing it from one, and you choose its endpoint, and you start sealing. And then along seal, while you are doing it, you ask yourself the question, does the geodesic distance decrease or not? When it does not decrease, as is in the case here, right? Think that you are sealing, removing the initial portion of this cut L1, nothing is happening. The geodesic distance is still the same. So you continue sealing. Can I seal the entire L1? Yes, I can, right? If L1 is actually removed completely, then the geodesic distance is still the same, because I have this cut and this cut, which are sort of supporting this upper geodesic. Okay, so then you continue. Then you take L2, the same. So imagine L1 is already removed. Okay, so let's see here. When I start sealing L2 from the top, yes, I can still do it because there is this L4, this diagonal, which supports the top. Okay, so I can seal L2, L2, L2 completely. L2 is removed. So now imagine L1 and L2 is removed, but nothing happened in my picture. So now let's look at L3, this one, okay? If I start sealing from the top, I cannot do it, because this would mean, right, if L1 is already removed. So if I start sealing L2, then immediately the geodesic distance between P and Q drops, right? I would be able to pass here by a polygonal, which is shorter. So I cannot seal from the top. But from the bottom, yes, I can seal, because still this L4 is sitting here and then L5 likewise. So I seal. Can I seal all the way up to the top? No, I cannot. Because if I removed L3 completely, then it means what I already explained, that I can pass like this. So this L3, I can only seal, in fact, this is the final picture, okay? So I'm sealing L3 from the top, I cannot. From the bottom, I can, up to this point. Then it turns out L4 now you cannot touch at all, and at 5 you cannot touch at all. Okay? So that is the procedure. Of course, if you start with different numbering of those different order of cuts, you are obtaining different final configuration. And in fact, here I started only with 2 geodesics. Observe that if I now, okay, so this is a certain order of cuts, then I end up just with those 2 cuts for that particular ordering. Then I still have only 2 geodesics, the top and the bottom. But in this picture that I just discussed, I end up with more geodesics. I end up with this one, still this one, which is the same as at the beginning, but I created a new geodesic, okay, which is exactly the same, supports the geodesic distance between P and Q. So this is the algorithm for sealing cuts, and it turns out, it's not hard to prove, that it is stable. That is, if you go with this, sealing from each side, from each vertex of each cut, when you go over all of them, and you start from the beginning again, there is nothing more to see. Okay? So you obtain what we call a stable configuration. That is, you really, in this process, the geodesic distance didn't change. There is less cuts. The original geodesics are still there. You created possibly more new geodesics. But now the configuration is minimal. That is, if you change any of the cuts, the geodesic distance is going to drop. It's a minimal stable configuration. You cannot do anything about it. So these are examples that I discussed. 3 creating 2 geodesics. This one in the here is even another. So since this new new set of cuts, is a subset of the original one, then if I find an isometry relative to this new smaller set of cuts, it will yield an isometry for the old set of cuts, right? Because just I have less degrees of freedom. I have less freedom, yes? So the original, I have more cuts in the original picture. So if I find isometry for the new picture with less cuts, then the other cuts are just hanging there, I say. They are not opening. They are acting as complete. So now I'm going to look for for an isometry for this stable minimal cut configurations. So it's not hard to observe that in the minimal configuration there are no loops. That is, there are no cuts that will create a cycle, because if there was, you could open one of them and the geodesic distance would be the same.
I have a maybe stupid question. So you showed that, I mean, depending on the ordering of your cuts, I mean, your labeling of the cuts, you get different configurations after your sealing.
Sure.
So is it clear that it does, I mean, whatever you do now doesn't depend on that process?
No, it depends. It depends. So I'm not saying that in my theorem that isometry is unique. I'm just saying that it exists, and now I'm giving you the procedure of obtaining it. Of course, different ordering of cuts will lead to a different final product, which still satisfies the conditions in my theorem. Okay. This is just an algorithm. I say you are given a Kirigamized sheet. You see some geodesics. I say order them. You order differently than I order. Not a problem. And then you start with sealing to obtain stable configuration. Your stable configuration different than my stable configuration. Not a problem. And then I tell you what to do with that stable configuration. Yes.
I was just curious, the number of cuts that remain once you remove the non-essential ones, is that the same for different ways of?
Can be, yes, can be. And you saw in the example here, right? Here, only 2 cuts. This is the same. I start with this one. Here, 2 cuts remain, and they are full cuts. So I completely removed 3 cuts. And here, 3 cuts remain. This is the full, this is full, and this is just a piece of the original cut L4. So anything, this is really in a full generality, anything can happen. So let's go ahead. So in the minimal configuration, two properties. First one, the graph has no loops. So that is really your set of cuts is a forest, which is the union of disconnected trees. Each tree is a connected graph, but it has no loops. Okay?
Yeah, so sorry. So when you do this deleting process, does it depend on the choice? I mean, the fixed P and Q. So if I choose a different P and Q,
when you choose different P and Q, there will be different geodesics. The whole picture is different.
yeah. So about that related to Philip's earlier question. So I mean, you're always thinking of one pair of P and Q, so not all simultaneously.
No, one P and Q, one P, one Q, but all geodesics simultaneously. This is like in Maha, you remember the original pictures? What I want to get a bowl. So I have a piece of paper, I want to put Kirigami's sheet. But of course, if I pull like this, I have a different things. So they say I have a square, and I want to grab here with a device, grab here, and then I want to pull. With respect to this, I want to put the cuts so that it works. Okay, so PQ fix, L fix. I have questions. Okay, so the two properties of the minimal configuration. That's one. It has no loops, so the whole cuts are split into trees, right? So a tree is a connected graph with no loops. And the second property, each vertex of the cuts that remain, actually, each vertex is a leaf, is a vertex of some geodesic from P to Q. Sort of it is intuitive, right? Because if I had no geodesic which passes through the vertex of a different cut, in a sense it's irrelevant, it's not supporting anything. Then I could start seeing from that cut, and nothing is going to happen. So every vertex that is a leaf, so the cuts may connect. But if I have a vertex, if I have an endpoint of a leaf that is just a leaf, there's a leaf, okay, endpoint of a vertex of a graph, that's a leaf, then it's going to support some geodesic. So some geodesic will pass. Based on these observations, you can in fact define a partial order on the set of geodesics, which just ordering them from the bottom to the top, so to speak. So you arrange your P and Q as sitting on the x1, E1 axis, and then you have the lowest geodesic, and then the geodesics, two geodesics are in this partial ordering adjacent to each other, when you cannot put anyone in between. Okay? So here, you see, this is the blue one is the first one, then let's say the red one is the next one, like this, right? There is no geodesic in between. In between, I mean that if you go by sigma 2 and then coming back by sigma 1, this is grosso modo the boundary of a positively oriented polygon in the plane. So this is sigma 2, then you have sigma 3, then you have sigma 4, and then you have sigma 5. Okay? So this is partially ordering. And now I'm going to label the trees and label the areas between geodesics. Okay? So maybe first look at this picture. So I will look first, I will construct my isometry between sigma 1 and sigma 2. But what happens between sigma 1 and sigma 2? I have some cuts, which in fact in this picture they are all single cuts, but in fact they can be trees. So I will distinguish between the regions in between those consecutive trees and inside the tree. So here is a better picture. I have a geodesic, say sigma r here, and I have a next geodesic sigma r plus 1. Okay, they extend from P somewhere here to Q somewhere there. Okay, I'm just drawing a piece. So this is some sigma r geodesic, this is r plus 1 geodesic. And in between, what is keeping them apart are those trees, are those cuts, structure of cuts. So I have some tree which I call Tn and another tree Tn plus 1. And I have regions between the trees. Okay, so this means that this region which I call here Pm is in between the rightmost path in the tree Tn and the leftmost path in the tree Tn plus 1. Okay, and the upper boundary is given by the geodesic. And I also have other regions which are inside the trees, because the tree is not just one single cut. Okay, so I have lots of areas, polygonal areas, for example, right? So this is some tree, right? Complicated tree. So you have areas like this between the cuts in the tree and between the upper and the lower geodesic. So now I'm going to say exactly how I construct the isometry in each of these polygonal regions. Okay? So here are the steps of the construction. So again, I have, say I have a geodesic sigma r and geodesic sigma r plus 1. They start from P1. What do I do on the first region? That is the region between, okay, P, between P and the leftmost path in the first tree that I encounter between those two geodesics. Okay? That is actually not difficult to see because this part of the geodesic and this part of the geodesic necessarily they have to be concave, right? In this form that's in the picture, right? If I had them opposite concave, this means that I would be able to shorten the path, shorten the geodesics. So the fact that here it turns, it follows from the fact that there is some cut here, extending here, which I'm not drawing because I'm only now interested in the region between sigma r and between sigma r plus 1. Okay? So basically what I can do using this convexity, I can just fold more and more on itself so that this piece, this path is folded on this straight line, and this path, this geodesic, is also folded in this straight line. So I'm just folding this, you see what I'm saying? I'm just folding this polygonal planar figure on itself so that the image of the original, of the initial piece of this geodesic and initial piece of this geodesic indeed is on one and the same segment, because this is what I want to do at the end of the day, right? I want that all the geodesics are sitting on one straight line, one segment. So the beginning, how to do it is easy. I use the fact that they have to be convex. Now, also when I am inside the tree, so I started like this. Now what happens here? Here is just some complicated tree. Again, what to do inside the tree is not a big deal, because inside the tree, basically you have this completely disconnected floppy pieces, and they are only attached to the geodesics, which must be, again, I have a convexity property. Okay, it must be like this. So there is no cut here, okay, because there is no cut. It cannot be concave, because it means I would be able to shorten the distance. Okay, so again, by convexity, I can just straighten each of them in a manner that all the image of this and the image of this becomes a straight line. So the real question is what to do in between, in those regions here, in between the cut, the tree, connected set of cuts, and the next tree. So how to arrange this, how to fold this piece, right, of my planar set. So let me explain to you, and this is really the key point of the construction. So let me explain to you how to construct U between consecutive trees in a simplified case when all the trees are single cuts. Okay, I told you that in general the pattern of cuts is arbitrary, but I can think of a simplified situation first when the cuts are non-intersecting. I have different lengths, but they have cuts like this, like this, like this. They are never touching each other, not at the vertices. So here, the tree, of course, is necessarily then just one cut. And then I have one cut. And I have a geodesic sigma r here. I have a geodesic sigma r plus 1 here. Okay? So I have already, by induction, by inductive procedure, I already constructed the isometry on all the pieces from P, which is somewhere here, up to this cut. So you see, I have rectified sigma r from P up to this point, and I have rectified sigma r plus 1 from P up to this point. So you can imagine a segment which is the image. This is the image of P, and this piece goes up to some point, because I've already constructed, and this piece of geodesic goes up to another point. So I know what is the image of this point and this point. This is already prescribed, the distance between them, how they are sitting on a segment. I cannot touch it. Now the question is, am I able to fold this figure inside here, inside what? Inside the golden bottom line sigma r plus 1, and this green sigma r plus 1, and then sigma r, and between this cut and the next cut, am I able to fold it in such a manner that this is rectified, but the distance between the image of this and this is prescribed, because this comes from the previous inductive procedure, previous steps in my inductive procedure. Okay, so question, can I always do it? But if you give me any distance that you want to achieve between this and this? The answer is no. There is no reason why it should be possible. But in this situation, you can always do it. And here is the argument why you can do it. So here is the proof. Okay, so you look at this here, this piece of the geodesic, and then you draw just a line from this endpoint of the cut that I'm discussing to this endpoint of the next cut that I'm discussing. Okay? This is going to be a convex domain. By convexity that we already discussed. Then you do the same thing at the bottom. So now you have two convex non-intersecting sets on the plane, they are polygonals. So there must be two lines, supporting lines, which are tangent lines, both of them at the same time, exactly two. And I call them psi A and psi B. So I am going to describe a folding procedure, which is folding this polygonal onto psi A, and there will be another procedure, similar, described by folding everything onto psi B, so that the image of both pieces of geodesics are on psi B, and in the first case, the image of both pieces of geodesics are on this line psi A. And then we will see that in one case, I am undershooting, that is the distance between the image of this point and this point is too small with respect to what I want to achieve, and in the other case, it is too large with respect to what I want to achieve. So therefore, by some application of the mean value theorem, there must be a line sort of in between this psi A and psi B, so that when I fold my figure onto this line, that I will achieve exactly the distance between the images of the 2 points that I want. That is the whole thing. So what is the folding? So let's look at psi A. Okay, so psi A is like this. See, it's here, for example, touching my bottom geodesic at this point, and it's touching my top geodesic at this point, intermediate point. So so again, this bottom geodesic is concave, inwards concave, and this one is also inwards with respect to the interior of the domain concave. Okay? So no problem. So I can, I put this piece up so that these two guys become straight, and then again I fold so that these 3 guys become straight line. And again I fold so that the image of this is onto this. And I do the same here. I start from this point, which is already sitting on my line sigma A. So I can fold so that this segment of piece of my geodesic again is on this line. Just a simple fold. And again, this piece here, again, I can fold so that the image of this is on here. So now let's see what is the distance between the image of B and the image of A under this construction. Okay, so I'm folding onto psi A. So this B is sitting here, and the A is sitting here. I know I cannot touch them. Okay, I'm just folding the rest. So the distance between V of B, V is this folding, this isometry that I'm constructing. Okay, so V of B, what is V of B minus V of A? Here in this picture, V of A is exactly A. So it goes like this. So I will go first from, okay, so here A and A prime are the same things. Doesn't matter. So I will compute the length of going from A to B minus the length of going from B to the image, so I mean this contact point B prime, to the image of B here. Okay, so this is this minus this. So this is the length of the distance, really the line, interior line between these 2 contact points, which I know is inside my domain, minus the length of the geodesic from the vertex, from the endpoint of the cut that I'm discussing, to this contact point. This is the difference. Now let's see what is the length, what is the distance of the image of this and this that I want to achieve. So by my inductive procedure, I know what is U. U is the final, is the isometry that I'm discussing, that I'm constructing here. Okay? So what is U of B minus U of A? Well, this is the length of the geodesic going on the top, so from from P up to B minus the length of the geodesic going from P up to A, of course. So can I compare now this distance, this difference with this distance, with this difference, which is okay? So here comes the definition of the geodesic and the fact that those are two consecutive geodesics in my partial ordering. So you see, if you go by up to here, by the sigma r up to here, and then go by this straight line, and then you continue with the golden geodesic, this is not a geodesic, because if it was a geodesic, or if it had a shorter distance, then the geodesic, the green one and the golden one, wouldn't be adjacent. So this is the comparison that you make, okay? You check the length of going along green line up to here, plus going here, and then continuing by the geodesic, with the geodesic length. So this must be greater or equal. In fact, it's strictly greater than the geodesic distance. Then when you compare the terms, it turns out that this ideal distance that you want to achieve is always less than the distance, the distance between the images of those 2 points when you project on sigma A. And then by symmetry, in fact, when you project on sigma B, you have the opposite inequality. So when you take a line in between, you can fold both pieces of geodesics under consideration onto that intermediate line. In fact, you can compute how this line looks like. You project, you fold onto this line, and then you achieve the distance between the image exactly that you want to match from the previous inductive steps. So this is just a simplified case. It's like the intermediate theorem, there is the line. But now in the general case, it is highly technical to construct. So now you have, again, you have the geodesic with the convex, concave part, another one with the concave part. But what bounds this region from the left and right are not just straight lines, which are single cuts when, you know, when all the cuts are disconnected, but they are some polygonal lines of cuts, which can be anything. So this is like the rightmost path in the tree on the left, and this is the leftmost path in the tree on the right. So now you remember what we had here. We have drawn this supporting. We use the fact that those two figures are just convex planar domains. So you had two supporting tangent lines, so to speak. So now you will not have tangent lines, but you have to look at the geodesics themselves, joining this vertex with this vertex. And then the geodesic from here to here. Okay, so of course here those geodesics were just straight lines, but now they are polygonal themselves. And it is possible to design an algorithm which, there are basically two case scenarios here. I don't want to bother you with this, so those supporting those geodesics may either intersect just at a single point, or they may follow a joint polygonal path. So this is also possible. And one can find an algorithm which simultaneously folds this pink area onto those supporting polygonal lines and at the same time rectifies them. So there is like there is an inductive, two inductive procedures playing with each other, in a sense that at the end of the day, you get the image of this and the image of this sitting on one of those chosen lines, but those polygonal lines are becoming straight, are rectified as well in this procedure. And again, you get some isometry V and isometry W, and one is undershooting with respect, and the other one is overshooting with respect to the distance of the image of those 2 points that is given by the previous steps in my inductive procedure. And again, there is some sort of intermediate value theorem which allows you to find an intermediate polygonal between this polygonal and this polygonal on which you should fold and rectify at the same time using the defined procedure from the proof of this result, and that gives you the final view. So Okay, so that's basically the proof. Here is just an example which shows that in this installment of the theorem, it is important to have P and Q on the boundary of the domain. If they are inside, then the theorem might fall because basically there's a configuration for which the distance between P, the geodesic between P and Q is such that if you rectify this one, in fact, you cannot rectify the other one. And the part of P and Q are not on the boundary. Basically, you have this tree-like structure of cuts going around this domain. So that's the result. That's a sketch of proof. There is lots of interesting questions. And out of this, in particular, one of the future project that we are pursuing is to study the structure of geodesics. In a Kirigami sheet, as the number of random cuts increases to infinity. So what can you do in this case? That's related to passage percolation problems.